Hi, I'll be doing today, and today we'll be going over contest three of last year or this year. So yeah. Okay, and then I guess we can just start from the elementary division. Okay, so main contents on contest three are Boolean algebra, and then there's also FSAs and regular expressions. So we'll be going over this today. So first for the elementary division. So for the first question, of the numbers between 20 and 27 inclusive, how many make this true? So the first tip I have for doing ACSL questions is always make sure you understand what the question is asking, because sometimes they're asking if it's evaluating to like false or if it's evaluating to true. So make sure you, or like how many expressions like something else. So make sure you actually know what's the problem is asking for. So this problem is asking for how many make this Boolean true. So it means not um x is less than or equal to 24 or x is less than 23. So that means it's has to be 25, 26, and 27 for this expression to be true. And because it's or, that means the other expression can also be true. So that means it can be 22, 21, and 20. That makes this part of the expression true. So we have 6. So that's how you do the first question. Okay, and then for the second expression, which ordered pair make this true? So that means we have not b times a plus b. So that means, or this squiggly line, not sure. That means, so b has to be 0. And then to make this part of the equation true, a must be 1 because b isn't 0, right? So then 1 times 1 is 1, which is true. So it would be, or 1, 0, sorry, because b is 0 and a is 1. Are there any questions so far? Okay, so moving on to this. Fill in the columns in the following truth table. Give the answers as the last column from top to bottom. So we want this column. So first we have a times b. So this is just like times is just and. So the only one that will evaluate to true is if they're both 1. So then we have 0, 0, 0, 1. And then we have not a. So it's 1, 1, 0, 0. And then we have these two added together. So then it's all of them. So you just add these two rows. So this is 1, this plus this is 1, this is 0, and then this is 1. And then we have not b, so then it's just the opposite of what we had. So 1, 0, 1, 0. And then we have this expression times this expression. So it's this expression times this. So we have 1 times 1 is 1, 1 times 0 is 0, 0 times 1 is 0, and 1 times 0 is 0. So we have 1, 0, 0, 0. And the next one, to simplify, we have not A times B. And this, so to simplify it, we want to distribute everything, right? To make it more simple. So then when we have not A times A, that automatically cancels out into 0 and you can cross that part of the expression out. And this works because no matter what value A is, whether if A is 1, then not A will be 0 and 0 times 1 is 0. Or if A is 0, then not A will be 1 and 0 times 1 will be 0 again. So no matter what, A times not A will be 0. So you can just cross that part of the expression out. So this whole not B. And then this part of the expression, similarly, we can eliminate the not B times B. And then it just turns into A times not B. And then because both, okay, so then you can use the distributive property and reverse it. And because you have not A times not B plus A times not B, it turns into not A plus A times not B. And this can be further simplified because not A plus A is always 1. And why does this work? Similarly to the not A and A, one of them must be 0 and one of them must be 1. And 0 plus 1, no matter which one is 0 and which one is 1, will be 1. So then 1 times not B will be not B. So then the answer will just be E. Are there any questions about number 4? No? Okay. Then we have number 5. Um, the Boolean algebra operator A and B is A XOR B is only true for the ordered pairs 0, 1, and 1, 0, which of the following is equivalent to not A XOR B. So not A or B means that it only works if A it only works for the other two pairs, which is 0, 0 and 1, 0, 1, 1. And then we'll just check through each expression and see which one fits into these two. So the first expression will evaluate to true when it's 0, 0 and when it's 1, 1. So that's a possibility. First one, it will always evaluate to, I mean, if A is 1 and B is 0, then it'll evaluate true, or if A is 0 and B is 1. So then that doesn't work. And this similarly doesn't work. None of these work because if A is 1 or if A and B is 0 or B is 1, it'll still evaluate to true, which doesn't fit in the situation that it asks for, that only 0, 0 and 1, 1 are the possibilities. So then the answer will be A. Then in the last question, in many elementary schools, teachers either teach math and science or social studies and language arts. So which Boolean algebra expression represents this relationship? So then let's just dissect the problem, right? So it says math and science. So that just means times, right? Because it's the and. So we have M times S. And then we have an or here, which stands for a plus. So we can just add an or here. And then we have social studies and language arts. So that's just SS times LA, right? So we just follow the problem and what it asks for. And then that's this one. Or not this one, sorry. This one. So it'll be D. Are there any questions about this entry? No questions? Okay, then let's continue on. So then we can go on to the junior. And this one is a little harder because it also has data structures in it. And what does this problem do? Okay, so for this one, first question, how many ordered pairs can make the following Boolean expression true? So for this, I would try to simplify this as much as possible. So how do we simplify it more? Well, when you have this, you can use a specific rule. And when you have not a some times something, you can turn it into not a plus not b. And how does this rule work? Basically, to separate something that's together, you just change the inside operator. So pretend there's a times here, and then you separate and add nots to each thing separately. So you have not a plus not b. And then now we have a times not b plus not a plus not b plus a. And what is this? This is four expressions. And why do I know this? Because not a and a, like we said before, always evaluates to true, right? Because one of them will always be one and all of them will, or all of them will always be one of them will always be one and one of them will always be zero. So together they'll be one no matter what, which is the equivalent to true. So then every single Boolean pair makes this true. So it'll be four. And to simplify this, we can use the rule above again and do not a plus not b. And to separate this out, we can pretend this is one value and this is one value. So we have not a plus not b plus not a again. And similarly to the rule that we did before, we can also turn this into a multiply instead of a plus and get rid of the overall not so that it turns into not b times not a, which is just not b times a because not a is just a. So then we have not a plus not b. And then we repeat a not a here, so then we can just ignore that. And then plus not ba. But then this isn't any of the answer choices, right? Because it can be furtherly simplified by distributing using the distributive property again, where we turn this into not a plus not b times 1 plus a, right? Because this just turns into this expression. And then this expression, 1 plus a just turns into 1 because no matter what a is, this will value to true. So we have not a plus not b. Are there any questions about this problem? No. Okay. So then for the next We have data structures. So for this question, we need to know what a binary tree is. So what is a binary tree? Um, well, a binary search tree is something with basically we like depending on the alphabetical order, we can organize the tree. So let me show this to you. If I show it, it'll make more sense. So basically, for the binary search tree, every element to the left of another element, like their child, will be less than. Every element to the right of an element will be greater than. So how does that work? We'll have, so to start, let's just draw the tree. I'll draw it down here because it's more room. So we always start with the first letter, and that's the first node. And then the next letter will be the next node. And then Q is bigger than E in the element alphabet, so then it'll be to the right. And then we have U is greater than Q again, so it'll be to the right again. And then we have E, which is less than or equal to E, so it'll be to the left, right? Because it's smaller. And then we have S, and this is a little interesting because S is bigger than Q but smaller than U, right? So then it'll be to the right of Q, but it has to be to the left of U. So it'll be a child of U to the left. And then T is bigger than S, but it's still less than U. So it'll be to the right of S, but less than U, so it'll go right here. We have R, which is less than S, but again bigger than Q, so then it'll go to the left of S. And then we have I, which is bigger than E, less than Q, so it'll be to the left of Q. And then A is self-explanatory, it's the smallest letter in the alphabet, so it'll always be on the left. And then we have N, which is bigger than E and less than Q, but greater than I. So it'll be here. Are there any questions about how we built the tree? The special thing about the binary search tree is there's only two children maximum for each node. It'll have either 0 children, 1 child, or 2 children. No questions? Okay. So then to count how many have 1 child, we can just look. This one doesn't because it has 2 branches. This one does. This one has 1 child. And this one has 1 child. Then everything else either has 2 or 0. The answer will be 3. Are there any questions about this? No? Okay. Given an initially empty queue and the following commands on the queue, what items are left from the rear to the front of the queue? So what's special about a queue is that it's first in, first out, which means that the elements, the order in which they are taken out of the queue will be in the same order as they were put in. So how does this work? Well, we put an F in, and then we have an E, and then an N. But then when we pop it, we'll get rid of the F because it's first in, first out. And then we add a C, and we push it, then we pop it, and then we add I, N, and then we pop again, and we have G, and then we pop again. So then we have NG. And then which items are left from the rear? Notice the question we have to pay attention from the rear to the front, so then it'll be GN because it's from the back to the front. So then for these kinds of problems, just pay attention to what it's asking for and make sure that you're following the correct order and just usually just stimulate the cues or the stacks for these kinds of questions. Are there any questions? No. Okay, let's continue. Okay, so next we have a what does this problem do? So basically we'll look at some code and then interpret what it'll do for these kinds of questions. So for this question, it'll be okay. What is the output when the following program is run using the following values of array? And note that array 0 has a value 2. So it's like this is 0th index, this is first, second, third, fourth, so on. So A is R3 minus R5. So then let's just look. 0, 1, 2, 3. So it's this one and then minus 5. So it's A is 2. And B is R6 plus R1. So 0, 1, 2, 3, 4, 5, 6. So it's this one plus this one. So it's 1 plus 3, which is 4. I see. And then we have array 6 plus array 1. So we have 4. And then if we output it, it should be 8. Let me see if something went wrong. Um, oh, then we output array. See, this is I didn't pay attention. I thought it would be output array A times B, but it's array output array A times array B. So array A is 0, 1, 2, and array B is 0, 1, 2, 3, 4. So it'll be 24. 6 times 4, which is 24. So for these kind of problems, just always make sure to double check that you're following exactly what the code is saying. Okay, for the next part, another what does this program do? What is the output when the following program is run using the following values of array R? Note that array 2, 3 has a value of 0. So this s equals 0, and from x is 1 to 2. So when x is from 1 to 2 is from this to this, and y is from 0 to 4, so 0, 1, 2, 3, 4 from here to here. If our x y is less than, so it's basically if this value is less than the value above it, then s equals s plus 1. So we can just check how many values is the box above it a higher value, yeah. So here this one is, because 3 is bigger than 1. This one is, this one is, this one is. 7 is bigger than 1, so no. 5 is bigger than 4, yes. 6 is not bigger than 2. 0 is bigger than 3. And these are the only ones that work. So we have 1, 2, 3, 4, 5, 6. So the answer will be 6. Are there any questions about this problem? No? Okay, then keep going. Okay, then let's go on to the intermediate. Okay, so we have Boolean algebra again, and data structures, and FSAs and regular expressions. Okay, so first for Boolean algebra, how many ordered triplets make this expression true? We can, again, for these types of problems, the best thing to do is to simplify the problem as much as possible so that you can make as little mistakes as possible in C. So we have A, not B. plus AC plus, and again, we can use this trick, so not A plus not B plus C. And remember, these two will just turn into not B because this can already represent this. And then we have, so then it's AC plus not A plus not B plus C. And then again, AC and C can cancel out because they can be factored into 1 plus A times C, which just turns into C. So then the simplified version of this expression is not A plus not B plus C. So then as long as one of these is true, as long as one of these is true, then the rest will be true. So that means only one expression can make it false, right? And that's if A is 1, B is 1, and C is 0. So then we have 7 ordered triplets makes this true. Does that make sense? Because as long as one of these is true, then well, it doesn't matter what the other ones is, it'll be true. So that means all of these have to be false in order to be false. Okay. Then next, to simplify this expression, this can turn into not C times not A, right? And then the not A will be repeating. So this part is just not A, B, not C. And this part, we can simplify this into A, B, A, not C. Does that make sense? Because this one, we can use the trick and this turns into a times, and then we just pull these two out. And not is A again, and then not is not here. So it's A, B, not C. And then we can factor out the B not C, and then it'll be an A times not A. I mean A plus not A. And then A plus not A is always 1, right? Because no matter what A is, if you add the not to it, it'll be 1. So then it just turns into B not C. So this one's D. And for the next one, employing a similar strategy to last time, let's draw the diagram out. Okay, so we have rug B7. So we have R. And then next is U. Is U bigger than R? Yes. So we have a U on the right, and then G. G is less than R, so we'll add it onto the left. B is less than G, so we'll add it on the left. Y is bigger than U, so we'll put it over here. S is bigger than R, but less than U. Be here. E is bigger than B, but less than G, so it'll be to the left of E. V is bigger than U, but less than Y, so E is bigger than B, but less than E. So they're equal to. And we have N is bigger than G, but less than R, so that'll be here. And lastly, I have S, which will just go to the left of S again. So then so you notice this question, it doesn't ask for like how many nodes like the last one have one child. It asks for how many nodes are at depth 2. So here you'll look. That means depth 2 means there's 2 branches going to it from the parent node. So we have 1, 2. So we have B, 1, 2, N, 1, 2, S, and 1, 2, Y. So it'll be B N S Y. And because it said left to right. Okay, and then next we have data structures again. And this time it's an initially empty stack, and we're doing the commands on a stack. So what's a stack? A stack means that it's last in, first out. So it's the opposite of a queue. The ones that are added more towards the end will be the ones that are removed first. So how do we do this? Let's just simulate the stack. So push A, push R, we just add them on, push C, then pop. Instead of removing from the front like we did for the queue, we'll remove from the back. We push H, pop twice, do the next two, and then push E, R, Y, and then we pop twice. So what item will we pop next? It's just this one, so E. So for these kinds of problems, just try to simulate it, and you can do it multiple times just to double check. Okay, so for FSAs, this is something we haven't seen before too much. And basically, we'll just check if they work for this problem. And how does this work? Well, to explain this FSA, an arrow means that you have to go through, you have to have this element in your string to make it. But then if you have an arrow going through the circle, that means that you can have it as many times as you want, or you don't have to have it at all. And then you have these next two and again. So it'll make more sense when we actually try them. So the first step, so if it's 0, 1, 1, 1, 1, this string, to test it, first we check if it goes through the first one, and it does, there's a 0. And then we check if it goes through the next values. And there's more than 2 ones, so then here, so then it'll pass through here. And then we have 0, 1, and there's a 0 and a 1 at the end. So this works. A works. And then B, we can check again. 0, yes. 1, 1, yes. And 0, 1, yes. And then C, we have 0, yes. And we have 1, 1. Then we don't have any zeros at all before a 1. So it does not work because it can never pass through this arrow. And then next, I have 0, 1, 1. We have 0 again, and then the 0 can go again, and then 1. So this works. And then the next one, we have 0, 1, 1, 0, but then we don't have a 1, so this doesn't work. And then we have 0, 1, 1 here, 1, 1, 1, and they can all go through this one, the arrow. We have 0, 0 again, and then 1, so this one works. So we have 1, 2, 3, 4 that work. Then for the last one, it's pretty similar, regular expressions, except for it's like different symbols. So to remind you, the arrow, I mean the asterisks mean it's similar to these ones, where you can have as many 0 or infinitely many as you want. And then this one means not. And then this is just you have to have it. Okay, so let's make more sense when we try it again. So J will go in here so it works. And then the lowercase j is inside of here because it's from F through M. So it's not in it because remember the little caret means not, so then that means this doesn't pass it. We have B, so K is in this, JK. U is also in T through V, T of V, and L is in also JK, J through P, JKL. And then we have A is not in C, it's not in F through M, so that worries A. Same with Z, 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 Z. And also 2 is also not in it. And then 4 is this value. So then B works. And we have L6, and this works because L is in here. And then we could skip this entirely because remember it's 0 or more. And then we have 6, so then it works. And then we have T, T, O, O, B, A. So T goes through here. T can go through here. Um, and then O can also go through because O is less than P. O can go. And then you would think B doesn't work, right? But B is not any of these values, so it does work. And 8 also, it completes the expression. And then we have maybe it's not. Okay, and then we have DST. So that's in here. But S is in F through, I mean, S is not in through here. X is also not here. Y, Z, and then 4. So this one should work. And this one should also work, right? Because 4 is this value. So I think all of these should work, but there is a problem. So then maybe hmm, I think B will not be working. It'll be C, D, E, F. And this one won't work because let's see the solution. Oh, it can only have one out of the 2, 4, 6, 8s. So then B doesn't work, and the answer will be C, D, E, F. So it's C. Okay, next, onto the seniors problems. This one I did. Okay, so we have Boolean algebra, data structures again, and FSAs irregular. So to simplify, I mean, how many order triplets make the following Boolean expression true? We've seen this question many times, and the strategy will be the same. We're gonna try to simplify the expression and then do it. So then how will we do that? Okay, so we have distribute it or try to get rid of the knots that are together. So we have A naught B plus A naught C plus, and then the trick that I showed before about you can simplify these kinds of expressions. It also applies to more than beyond just two booleans. Instead, you can also do it to three, so it just turns it to not A plus the opposite of not B, so it's B plus not C. And then this also turns it to not B plus not C. And this expression seems very complicated, but it's actually not complicated because notice how there's a B and a not B. And that just turns into 1, right? Because no matter what value B is, 1 or 0, one of them will be 1. So then all expressions where are true. So it'll be 8. Okay. Moving on to the next question, we have simplify the following expression. So then and we can simplify this by pretending this is two parts and separating it. So we have not A times not. I mean plus, sorry. Because there's a times in here, yeah. And then this times A times not B plus not C. So just A times not C. And then times not A plus not B. And then this one can be further simplified into B times C. I mean, not B times C. So we have not A. Let's just erase B times, not B times C. And then now we have to try to distribute these values and see how they simplify, which seems pretty complicated, but then you'll see it gets simpler. So first, let's distribute this times this. And notice how it's not A times A, which always evaluates to 0, and same with this one. So then we can just get rid of this not A. And then similarly, we have not B times not BC times A not B. So this one we will need, so it's A not BC. But then again, not BC times A not C will evaluate to 0 because not C times C will be 0 because one of them will be 0 and 0 in anything is always 0. And then and this one, we have A and not A will always be 0. So it just turns into A not BC. We have this one. Okay, now build a binary search tree for this. Again, we'll just build it and then see how many nodes have only one child. So we start with the parent, then E is bigger than B, so then we go to the right. We have A is less than B, and then C is less than E but bigger than B. H is bigger than E. V is also bigger. O is bigger than H but less than V. L is bigger than H but less than O. L is again smaller. E is bigger than C but less than E, so. And then Y is bigger than V. And then we have B is bigger than A but less than B. It's this way. And A is less than A. And then we have two more L's, which will go over here. So how many nodes have one child? Let's count. So this one doesn't, this one doesn't, this one doesn't, this one does, this one does, this one does. One child just needs one branch is coming out of them. So 1, 2, 3, 4, 5, 6. 6 will be the answer. And then given, this is something we haven't seen before, given the following tree, find the values that can be used in place of the question mark. So that just means what values can this one be? So it's kind of like the opposite logic of we've used before. So this one just means that because it's to the left of Q, we know that it must be greater than or equals, I mean less than or equal to Q. And then it's also to the left of T. But we don't need to consider that because if it's less than or equal to Q, it's already must be less than T because Q is smaller than T. So we use the tighter boundary, so it's less than or equal to Q. But then it's to the right of M, which means it has to be greater than M. So then it will be A. Does that make sense? Okay. And for these FSAs, lists all the strings that are accepted. So this one has two possible paths. It can go through here or go through here. So we'll have to be careful of that when we're testing it. So this one, we have A, and then B can go through here, and then A, D, A. So this one works. B is A, it goes through B once, and then it has to go this way because A, and C, but then it has an A, which it can't go anywhere, so this one doesn't work. And A, and we have C, D, D, C, A, B. So this one does work. And we have A, C, C, A for this one, so it does work. So then it'll be A, C, D. And then for regular expressions, we could test the ACSL board and game, and we see which one satisfies this expression. So we have checkers. So then my strategy when I did this problem is most of them I just saw if they went through here and just ignored the first test case. So C goes through, not S. None of these are S. So then we have H, E, C, K, and they all pass through. But then we have to have a value, we must have one value that's not in O through T. So R and S don't pass, but E passes. So then I would put E as that value. And then R and S are in O through Y, and they can go on. So then this one does work. Similarly, for chess, C and H can go here. E can go in here because not an O through T. And then S and S can go here. And then Monopoly, similarly, we can have MONOPOL. They all are in not S. And then Y is not in O through T, so it can go here. Cribbage, similarly, CRIBBAG, they can all go through not S, and then E can be in not O through T, so it works. Bingo, we can have BIN here, G here, and O is here, O through Y. Uno, we can have U is in not S, N is in not O through T, because N O P, and then O is here, O through Y. And then, so then Uno works. And Racco, we have RAC can go here, K can go here, and O can go here. Duo, D goes here. I don't know. D has to go here because U and O are both in O through T. And then, or no, U isn't. And then U and O can go here. But also for duo, D can go in not S. U can go in not O through T, and then O goes here, the last part. So all of them work. Are there any questions for any of the short problems? Because will be all of the short problems. Then let's go on to the coding problem. So for this coding problem, basically they explained to us what a sinusoidal triangle pattern was. So just to simplify it and instead of reading all the problems, it means they write out all the numbers, but they go 5, 4. If it's a 5 wide, then it goes 5, 4, 3, 2, 1, and then it goes back up in width and then goes back down. Or it could be like 3 or 2 or 1. I mean, it couldn't be 1, but it could be like 2, 6, and so on. And then notice how the numbers snake. So it goes 1, 2, 3, 4, 5, and then 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, like this. And then, so then the Manhattan distance between the two numbers and a sinusoidal triangle is how far the numbers are from each other in terms of the horizontal and vertical direction. So then, for example, if 1 and 16, the Manhattan distance would be, first of all, horizontally, they're 1 apart. So it'd be 1 plus, and then vertically, they're 1, 2, 3, 4, 5 apart. So then it'd be 1 plus 5, which is 6. And same with 17 and 2. So then, how do we do this problem? Well, to do this problem, we have to stimulate building the sinusoidal triangle, and then we can just test it. So how I did it and do it is here. I'll explain this Python code. Basically, first you wanna find which one is bigger and which one is smaller, so that you know both the numbers that you want to look for. And then I made an array and I stimulated adding all the sinusoidal numbers onto the array. So I had a 2D array because for this, you want to know both the vertical and horizontal distances. So you would need a 2D structure to be able to show that. And then I also added a increasing and decreasing variable because you don't know if you're going up or down. And then I made it everything in a while loop. So then this temporary array is just the array that we're going to be adding to the final array. So then we have for something in a range of L, and L is just how long we want to be going. So how many, so depending on which row we're on, it'll be like 5 or 4 or 3 or however long we need the array to be. And then we'll append it. And this D variable is for if we're increasing or decreasing, because no, remember it's snaked, like it snakes from here to here to here and so on. So then the D variable is to keep track if we have to add it to the end or insert it in the beginning. So like for example, for the first row, it would be like we add the next number to the end and the next number and so on. And the second row, we want to add the new numbers to the beginning of the array. And then we also have to increment the index that we're looking at. So we start with 1 and then we just go on. And then we just append the temporary to the array. And then we make the opposite because if we're increasing, we want to start decreasing. And if we're decreasing, we want to start increasing. And then we just check if I is bigger than A, then we break because we don't need to add any more indexes into the array. And A is the maximum between M and N. So then also we have to check something if length temporary array is equal to 1 or if it's equal to the width. That means we have to make decreasing or increase the opposite. And why does that make sense? Because we have to make sure we know when we're decreasing in length when we're building it or when we're increasing it, so that we know when to change L. And that's here. So if it's decreasing, then we make L smaller, and otherwise we make L bigger to make the sinusoidal shape. And then finally, after you're able to build your sinusoidal shape, which is, in my opinion, the harder part of the test, then you can loop through the array. And for ACSL problems, the inputs are usually not very big, so you usually won't run into like time complexity issues. So then you can just do a double for loop and search through the array, and then if it's equal to A, then you just set AR and AC to be these values. And then if it's equal to B, then you can set them to be the values. And then finally, to finish the problem, you just return the absolute value of AC, and AC stood for A column, BC is B column, and then plus the absolute value of A row minus B row. And if you run it, you can see that, yeah, it works on the test cases. So then, yeah, that is basically how to do the short. Oh, we can do a test case just to see if it works. Let's try number 5. So the answer is 4. I think that there's something wrong with the input. It's okay. We can just put it in. 8, 200, 180. And then yeah, 4 is printed. And the answer is 4. So are there any questions about the coding problem? No questions? Okay. So that was basically how contest 3 went. Are there any questions about contest 3? Oh, okay, thank you. That'll be it for class today then. Have a good